Alrighty, well, while it's still week one in this statistics course, it seems like we ought to get around to talking about probability. Probability is so central to all of statistics. So, probability, what is it? I'm going to give you some definitions to get started. Not many, but before we actually define probability itself, let's define an outcome. Outcome is a very important word that we use a lot. An outcome is basically just some clearly defined result, and it's best if I give examples, I think. A clearly defined result, such as, well, we might be flipping coins. He gets heads. Might be a result that we're interested in. We might be rolling dice. He gets a 6. That would be a particular outcome we might be interested in. We might be playing with a deck of cards. He draws, what are we going to draw? How about the Ace of Hearts? He draws the Ace of Hearts. That might be an outcome that we're looking for. Of course, it could be he draws a heart of any kind. It could be he draws an ace of any kind. It could be all kinds of things, right? You got lots of choices here. If you're working for an insurance company, that's where the big bucks are. Working for an insurance company, you got to figure out things like, what's the probability that this teenager who just got his license is going to crash into a tree in his first year? That's important. I laugh, but it's actually very, very serious and important. You got to be able to figure these things out. What is the chance he's going to crash into a tree and that we're going to have to pay for things and stuff? Maybe you're some kind of into political stuff. You want to know the probability that she votes, whoever she is, for Sally, whoever she is. She votes for Sally. A lot of people are very interested in, working out who's going to vote for when, who's going to vote for who. Maybe you're trying to sell something. They all drink Wink. I have no idea what Wink is, but I remember seeing a sign for it. Drink Wink. So whatever it is. They all drink Wink, whatever. So it could be anything. I'm just going to put a big, gigantic, etc. here because it could be almost anything. But it's clearly defined. You're looking for something to happen. I'm going to get a heads. I'm going to get a 6. I'm going to draw the Ace of Hearts. I'm going to crash into a tree. Woo! Whatever. Okay, so those are what outcomes are. Then I can start talking about what is the probability. First of all, probability is referring to an outcome. So probability of an outcome. Or it could be a set of outcomes too. You could be looking for the chance of getting a 5 or 6, but let's not worry about that. Probability of an outcome, well, it's a fraction. And that's why we spent 2 days on fractions, decimals, and percents. Probability is a fraction, and it's defined like this. You take the number of outcomes that are considered, and I'm going to put this word in quotes, favorable. And I say favorable because you might be looking at the probability of running into a tree, but I don't know if you want to call that favorable, but we'll call it favorable in a mathematical sense of some sort. So the number of outcomes considered favorable are the ones you're looking for or whatever, over the total possible number of outcomes. It's that ratio. The number of outcomes that count as winning, so to speak, is one way I think about it, divided by the total possible number of outcomes. And I think I'll put this in like a double brackets thing like this. There we go. Let's change colors too for a little bit of emphasis. Notice, this is important. This is actually important. Let's write this down before I forget. All of your counted outcomes, because you're counting outcomes, that's how you determine a probability. You determine how many ways can I draw the Ace of Hearts or whatever. How many ways can I draw anything at all? You're counting things. How many outcomes are possible this way or that? So all counted outcomes must be, capital must, be equally likely. And we'll see what this amounts to as we go through some examples here. But they must be equally likely. This is kind of like, remember a fraction in the first place? We say, you put the part over the whole, and one of the important things was make sure all the pieces are the same size, right? It's not a real fraction if the pieces aren't all the same size. Well, this is a fraction. That means we need the pieces to all be the same size. So all the outcomes need to be, quote unquote, the same size. They need to be equally likely. They all have a 2% chance or whatever. You can't have one outcome has a 2% chance, another outcome has a 27% chance, and say, it's 2 outcomes. No. You want to count equally likely outcomes. So that's important. I'll put that there right now. And then here's another note. Another thing worth noting. When you make a fraction, when you determine a probability, you're always going to get an answer that lies somewhere between 0 and 1. And that's a good way to say that. The probability has to be between 0 and 1. It can be 0. If your probability is 0, what that means is that it's an impossible outcome. It ain't going to happen no matter how much you try. If your probability comes out to the number 1 or 100%, it's a certain outcome. It's pretty near, well, it is. It's guaranteed to happen. Certain outcome. It's not even pretty near. It's guaranteed to happen. And then, of course, you can have anything in between. You can have probability of a half, a probability of a fourth, whatever, probability of 7 over 33, whatever. They're all fractions. They're between 0 and 1 is the important fact. I'll just call that fact. I'll call that, in fact, I'll call that an important fact. So this is what we need to work with here. This idea of probabilities. They're fractions. You make a ratio. You count the number of outcomes that are favorable. That goes on top. Favorable meaning you're looking for that to happen. What's the chance of that happening? And then on the bottom, it's anything that could happen. The total possible number of outcomes. Whether it's what you're looking for or not. What can happen here? You add up what's the total things that can happen. How many would count as a win, so to speak. How many am I interested in, looking for, whatever. Make that fraction. It will have to be between 0 and 1. And make sure your outcomes are equally likely. Okay, these are the most important things about probability that you need to understand. Next, you need to start working with some examples so you can get the hang of this stuff. So I got 8 good examples here. Biff flips a coin. Good old Biff flipping a coin. What's the probability it comes out heads? Well, the first thing I want to do is I want to list the possible outcomes. There are 2 possible outcomes when you flip a coin, right? You're either going to get a heads, boink, or you're going to get a tails, boink. So you got 2 possible outcomes. Now, if it says what's the probability of coming up heads, that's kind of saying that for some reason we're determining heads are favorable. Maybe if you roll a heads, you win $50. I don't know. Roll a heads, flip a heads. But whatever. Heads is what we're looking at. It's what we're interested in. We're going to call it favorable, even if it's not actually favorable. It's what we're looking for. We're looking for heads. So the probability of heads, and here's our little notation for that, P of H. So P means probability. This parentheses is, well, in algebra, it's a function notation. It means of getting heads. P parentheses H means probability of getting heads. Is you put the number of possible outcomes on the bottom. There's 2 possible outcomes. How many are favorable? Just the 1. You're actually done. That's it. The probability of heads is 1/2. If you want, you can make it a percentage or even a decimal, 0.5 or 50%. Cool. That's it. That's how it works. Count your possible outcomes. Make a little ratio here. How many you're looking for, how many are possible. Now, a couple more terminology, concept type things we can talk about down here in green. What's this law of large numbers? Well, first of all, ask yourself, what does this really mean? Hey, I got the chance of 50% getting heads. What does that really mean? Does that actually mean that you will get heads 50% of the time? Not really. You could flip heads twice in a row. That's not 50% of the time. You could flip heads 3 times in a row. That's not 50% of the time, right? So it's only if you keep flipping forever, if you keep flipping over and over and over and over and over about 8 gazillion times, then you would expect pretty much the same number of heads and the same number of tails. You would expect heads are about 50% of the results. That's called the law of large numbers. It means, well, let's put it this way. When you flip the coin over and over, and I do mean for a long time. We might do this at the end of the course. We can get Excel to flip coins for us. And you could find that you could flip a coin 10,000 times. Do you have 5,000 heads and 5,000 tails? No, you don't. It's amazing. But it's getting awfully close to 5,000 of each. It might be 4,950 of each, or of one, and whatever. But when you flip the coin over and over for a long time, emphasize the long, you expect to get closer to 50% heads, and 50% tails. And you can say that because tails is the only other possible result. So heads and tails, right? So if the probability of heads is 50%, well, it's a 50-50 for heads or tails. Again, you're not going to necessarily see that if you just flip a handful of coins, but if you flip a cajillion coins, you're going to come out, and again, it's not even going to be exact, but it should be awfully close. Okay, that's the law of large numbers. It's like, yeah, you can trust this in the long term. You might not be able to bank on it in the short term, but in the long term, it's going to work. Okay, so if you were to graph this, for example, if you were to make a graph, here's the probability, and it can go as high as 1, and it can go as low as 0, and this will be the number of flips going this way. Well, on your first flip, maybe you got a heads, and so it looks like you got a 100% chance of getting heads. And on your second flip, you got a heads, so it still looks like a 100% chance of getting heads. But then on your third flip, you got a tails, so now you're, I don't know, third or something chance. 2/3? I don't know what you would be. Yeah, you'd be at 2/3, wouldn't you? Because you would have got it 2 out of 3 times. Let's just kind of do that. 2/3, and then maybe it would be half again, and then maybe if you kept rolling tails, it would dip under, but then you'd start rolling. Anyway, it's going to bounce up and down is what I want to say. And as you get out here, what are you doing? As you get out here to a very, very large number of flips, you kind of expect that any scatter you have over here is going to start really smoothing out and leveling out at just about 50%. Law of large numbers. Statistics works if you keep doing something over and over and over and over and over a lot. Okay? That's one of the things you want to keep in mind. 90% doesn't mean 90%. It means, well, eventually 90%. That's what it kind of means. No guarantees. Yeah, that's just making the point that, theoretically, and I've had this happen, I need a heads to win the game, so of course I roll a tails about 18 times in a row. So theoretically, you could flip tails forever. It's not likely. Not likely. In fact, a mathematician would probably say, oh, and forever, you're talking infinity now. Yeah, it's not going to be. But no, theoretically, let's say it forever minus 1. Theoretically, you could flip tails forever. Not likely, but it's possible. That's why we say no guarantees. Nothing is guaranteed in statistics. That's what makes statistics kind of an ugly form of mathematics, because you can't really know for sure, certain, bet your soul on it. You can't quite know what the heck's going on. But, law of large numbers says, well, you expect it to work in the long run. Independence. Here's another good word. Independence. The reason that we don't have any guarantees is the coin, or maybe I'll say each coin flip, is completely independent of whatever happened in the universe before then. It does not care. Hey, I just flipped 97,000 heads in a row. You think I'll get another heads? It doesn't care. It does not care. Each coin flip is completely independent of whatever happened in all the eternity beforehand. It does not matter. It's always 50% chance every single time of all of the eternity beforehand or whatever. So in other words, when you're about to flip the coin again, it's a 50-50. No matter what. That's called independence. The coin is independent of you, independent of what you expect, independent of what your brain is telling you has to happen. It doesn't have to happen. Okay, it doesn't have to happen. That's what I'm trying to get across. But let's just keep falling back on this. Law of large numbers says, well, it will in the long run. It will. In the long run, we expect that. Yes, we do. We expect. Can't even guarantee it, but we expect. Anyway, I hope I'm making some good points here about how careful you have to be with this probability concept, right? It's kind of a measure of what you expect to happen, but again, no guarantees. So, example 2. A child is born. I should have said a star is born. That would have been cooler, right? A child is born. So what's the probability that it's a boy? Well, I think we can agree there are 2 possible outcomes. It could be assigned a gender, or is it gender or sex? I don't know the word. It could be assigned a whatever of boy at birth, or they could be assigned a whatever of girl at birth. You don't really get assigned anything else, do you? I think it's always you're assigned boy or girl. Okay, so there's two possible outcomes. Two possible outcomes. So, you want a boy? Well, there's one out of two, right? So 1/2. Question mark. Do you think it's a half? And no, I'm not trying to get political here. I'm not talking about other kinds of genders or sexes or whatever the word is I'm supposed to use. I got to brush up on this stuff, I guess. But anyway, before I go doing this probability stuff. But anyway, is it a half? And the answer is not quite. Not really. Not quite. And what's the problem here? The problem here is that having a kid, I should put it this way, having a kid is not exactly like flipping a coin. You might make an argument that it kind of is, that you're going to get roughly half boys and half girls. But if you look at the data, see, the thing is, there's all kinds of, what do you want to call it, genetic, biological, environmental, biological, I like that, biological, etc. stuff going on. It's not just a coin that's going to flip and come up on one side or the other. You got a kid in there and it's growing and there's all kinds of genes being expressed, and who knows, might have something to do with what kind of juice you drink in the morning. I have no idea, but there's factors. So, like, for example, let's say you discover a new species. You discover a new species of frog. Do you think you'd be correct in assuming that baby frogs in this new species are 50% boys and 50% girls? You don't know that. How do you know you didn't just discover a species that has 3/4 girls and 1/4 boys? You don't know, right? You don't know. You can't say, oh, it has to be, because it's not a random event. It's a biological event. It's a natural event. It's something weird going on there. So if you discover a new species of frog, not safe really, and I'll say not safe really, to assume 50% of offspring are boys and 50% are girls. It's not safe to assume it. You have to observe, measure, if you will. You have to observe or measure. With humans, it turns out it's not 50%. With humans, it's a lot closer to a 49-51 split, where you get 49 girls and 51 boys. And there's theories about this. They say, oh, evolution, more boys die, so we have to have more boys. Okay, whatever. There could be a reason like that. I don't know. So 49-51. So you're closer off saying it's a 49% chance of having a girl and a 51% chance of having a boy. See what I mean? So this idea of equally likely lets us do math stuff. If these were equally likely, we'd be able to say, oh, wow, there's one chance in two. It's a 50-50. But I'm just saying, you got to be careful about this whole equally likely thing. It might not be equally likely. You might have to do some experiments, so to speak. You might have to have some boys and girls or whatever, and then just see what's coming up, what's happening here, what's going on. Okay, so that was a warning, if you will, about, again, this concept, and I'll highlight it again over here, of equally likely. To make a simple fraction, you have to assume that the outcomes are equally likely. And maybe you can. Flipping a coin, you probably can. By the way, there was a guy, he was in prison for like years and years and years, and so he decided to flip a coin over and 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 over. I don't know if it was 10,000 times or 100,000 times. He flipped a coin a lot, and he proved that, yeah, it's about a 50-50. So you could say it's experimentally verified that a coin is a 50-50. Okay. So we're grooving on probability here. We're chewing on it, trying to understand this concept. Okay, example 3. The town of Mooville has 90 cars. 90 cars. There's blue, there's red, there's white. Blue, red, and white cars in Mooville. So a random car from Mooville drives by. What's the probability that it's a blue one? I'm in the mood for dark green. What's the probability that it's a blue one? Well, you might say the possibilities are... could be a blue car, could be a red car, could be a white car. right? And you're going to pick a car at random, so to speak. A random car drives by and you look at it. So you observe one car at random. What's the probability that it's blue? Wow, what do you think? 1 in 3. There's 3 colors. One of them's blue. 1 in 3. Well, I hope you're getting a little bit paranoid here. And you're saying, I wonder if I could say that. You could say that if. If what? We only know that. Or maybe instead of saying we only know that, I'll say it this way. We could only conclude that, or we could only say that, if we knew we had the same number of each color. Get it? It'd be equally likely that way. Same number of each color. It says there's 90 cars. Well, if we had 30 blue, 30 red, and 30 white, then it would be equally likely that you're either going to get one of those 30 blue ones, or one of those 30 red ones, or one of those 30 white ones. If that were the case, you could say 1/3. But is that the case? No, they don't tell us that. They don't give us any knowledge of that whatever. And because they're not giving us any real knowledge of that, we have to say that it cannot be determined, indeterminate, something like that. We don't have enough info, that kind of thing. We need to know how many cars are there of each color. Then we can start making some ratios. Okay? So, yeah, be careful about this equally likely stuff. Number 4. Okay, this one we're going to be able to answer. We can calm down a little bit, relax a little bit, and here's a problem we can actually do. There's an urn, and it contains marbles. And 50 of the marbles are green, and 40 of the marbles are red, and 30 of the marbles are blue, and 20 of the marbles are purple. See, they're telling us how many of each color we have. That's good. So if one marble's drawn at random, what's the probability it's blue? Well, you're just going to draw one, right? So what are the possible outcomes? You could get one of those green ones. You could get that green one, that green one, that green one, that green one, that green one. There's 50 of those. Maybe I'll just kind of put it like this. 50 of these. You got 50 letter G's. Then you've got 40 of these red ones, so you could think of that as listing out 40 R's, I suppose. 40 of those. And then you got 30 blue ones, so that would add to your list. 30 blue ones, so just imagine there's 30 B's here. And you've got 20 purple ones, so just imagine there's like 20 letter P's over here, right? So you got to picture, how many marbles are there? 50 plus 40 is 90, 100, 110, 120, 30. There's 140 total marbles here. So, what was I going to say? You have to consider each marble individually, kind of. There's 140 marbles here. Okay. So they want to know what's the probability it's blue. Well, the probability that it's blue, the one marble that you choose at random, is going to be, take the number of blue ones that you could pick, and take the number of the total number of marbles that you could do. How many blue ones are there? It's over here. There's 30 of them. There's 30 letter B's. Whoops. Come on, you. There's 30 blue marbles. How many total? Well, there's 50 greens, and there's 40 reds, and there's 30 blues, and there's 20 purples. And so that comes out to a fraction of 30 over, that was 140, right? Right. And then we could reduce. Might as well at least cancel the zeros or cancel the tens off. It's a 3 and 14. That would be the reduced fraction form. You can make a decimal by saying 3 divided by 14. You get about something like 0.214. And to make a percent, you would go like this and say 21.4%. So there'd be about a 21.4% chance that you would draw a blue marble. If you kept doing this forever and ever and ever and ever and ever, over time, 21.4% of your draws would be blue marbles, we think. We expect. We fully expect. Okay, so that's good. So equally likely outcomes means you can rock and roll, you can boogie. I think I got like 4 more examples. Okay, we better get moving here. Let's get moving. Example 5, Bonnie tosses a fair 12-sided die. Okay, that word fair, that's a good word to see. Fair is telling you all results are equally likely. That's what it means. A fair coin, a fair die. It means all results are indeed equally likely. It's not like there's some kind of a weird weight on one side or something. So, okay, before we even think about these questions ABC, what are the outcomes? We can list all the outcomes now. 12-sided die, well, I'm going to assume there's a 1, 2, 3 on each side, right? So you could get a 1, you could get a 2, you could get a 3, you could get a 4, you could get a 5, you could get a 6, you could get a 7, you could get an 8, you could get a 9, you could get a 10, you could get an 11, you could get a 12. Those are all the outcomes, and they're all equally likely. That's a good list to have. If they're all equally likely, we can start making some fractions, making some probabilities. So the probability, and note this nice notation here, right? It's like that function notation again. Capital P stands for probability. Parentheses stands for of. The probability of what? Getting an even number on your roll is, well, you would have to count the number of even outcomes over the total number of outcomes. Even outcomes, 1, 2, 3, 4, 5, 6. There's 6 even outcomes. Total outcomes, 1, 2, 3, 12. There are 12 total outcomes. And so actually that's a straightforward 6 over 12 is 1/2. That's a good answer. You could make it 50% if you want. So the probability of getting an even number on a roll of a fair 12-sided die is 1/2. Part B. Probability of 4 or higher. You want to try this one yourself? You could pause, Pause and try it yourself. Try the next two yourself. 4 or higher. Well, you look at your outcomes here, your list of outcomes, and you say, well, that's a 4. Or higher. Well, that's higher, 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 higher. So I'm counting all of these over here. 4, 5, 6, 7, 8. Let's see, I should count. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 that are higher. So actually I should put it like this way. How should I put it? Well, I'll just count. There were 9 that were 4 or higher out of 12, and that would reduce to, cancel 3's here, 3/4. That's cool. How about this last one? Probability of less than 8. Maybe I'll write it this way. It's a little bit easier to write. The probability that the result we get is less than an 8. Well, boy, I hope this thing's still working. My computer blacked out. There it is. Okay, anyway, probability that it's less than 8. Well, erase all this stuff. Okay, and count up less than 8. Well, an 8 is not less than 8, so don't count that one. You can count the 7, the 6, the 5, the 4, the 3, the 2, and the 1. So it's actually 7. 7 out of 12, and that won't reduce, so just circle the 7 out of 12. If you want to do 7 out of 12 because you're interested in the decimal, it's a point like maybe 583, rounding to 1 decimal place, which as a percent would be about 58.3%. Sometimes fractions are nice. 7 and 12, I think, is a little easier to think about than 58.3%. That's a little harder to think about for me. Because 7 out of 12, I just say, well, there's 12 things, and 7 of them are mine, and the other 5 are not. 58.3 is like, I don't know. All right, let's do this other one. What do we got? Oh, I wanted to do this deck of cards one because in a lot of times in these probability statistics classes, some people haven't seen a deck of cards. So it's like, well, this is going to make sure you see a deck of cards. This is a standard deck of playing cards. You will notice that there are 4 what we call suits. All of these cards here all have the same kind of mark on them, and we call that mark spades, that little, that thing. That's a spade. So those are, there's 13 spade cards. These, you might guess, are called hearts because they have little heart marks on them. These have little diamond marks on them. So what do we call that suit? We call that the suit of diamonds. Now, I don't know what you'd want to call that, puppy toes or something. Well, it's actually called clubs. I have no idea why it's called a club, but it's called a club. And that's called an eraser. Come on, you. Okay, cool. So those are your 4 suits. So you got 4 suits. Maybe I'll even put that down. 4 suits. And then in each suit, you've got 13 cards. These are the ones, which another word for one is ace. So these are called the aces. And obviously the 2s, the 3s, the 4s, you can see what these are, all the way up to 10. So 2, 3, 4, 5, 6, 7, 8, 9, 10s. And then what are these things called? These, by the way, are called the face cards. But the J stands for the jack, and the Q stands for the queen, and the K stands for the king. And all of these together are called face cards. Not facial, but face cards. Face cards. Okay, so that's what you got for a standard deck of cards. Notice there's 4 suits, 13 in each suits. 4 times 13 is 52 total cards. Sometimes they throw in a couple extra cards called jokers. Let's not worry about the jokers. So 52 total cards. And what you usually do is you shuffle the heck out of them and you deal them out and you play a little game. So let's do this instead. Let's play probability games. So the deck is well shuffled. That's what it's saying here. The deck is well shuffled. Shuffle, well shuffled. Shuffle for a long time. And then deal one card. So what is the chance that one card is a heart? So you want to know I'll write it like this. The probability of a heart, well, what you would have to do is you would have to count up equally likely outcomes now. The number of outcomes that are hearts out of the total number of possible outcomes. How many are hearts? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There's 13 hearts. Remember, there's 52 in the whole deck. Let's erase those scribbles. 15 in the whole deck. 52 in the whole deck. And actually that reduces. 13 goes into 52 exactly 4 times. So it's actually a 1 in 4. Which you could probably figure out by saying, well, every suit has the same number of cards. So each suit is an equally likely outcome. And there's 4 suits, so it's a 1 in 4, right? You can think of it that way too. How about face cards? Probability of a face. Well, you'd have to count up how many face cards are there and how many total cards are there. How many face cards are there? Well, they're over here. You got to count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 of them suckers. So 12 face cards. Again, the whole deck is 52. You could cancel 2s here, 6 out of 26. You could cancel 2s here, 3 out of 13. So it's a 3 out of 13 probability of getting a face card. If you want to... Now, 3 out of 13 is a little hard to think about. As a percent, that would be something like 23.08%. 3 divided by 13, slide your decimal. Probability that it's an ace, not a face, but an ace. Well, you'd have to count up the number of ace cards, not face cards, ace cards, over the total number of cards. The aces are over here. 1, 2, 3, 4. You got 4 of them. So this will be a 4 out of 52. And it turns out 4 goes into 52 evenly. It goes 13 times. So that reduces to 1/13th, or a 1 in 13, or as a percent, 7.69%. 1 divided by 13, slide your decimal twice, is a 7.69% if I round. Okay, cool. So good. Now we know what a deck of cards is, and now we're getting some confidence now because, you know, our faith in the universe is what is it? Enhanced? Increased? Bolstered? I don't know. Because look, we're getting answers. Okay. None of that trick equally likely stuff. All right, 2 more examples. These are actually very important examples. Birdie rolls 2 6-sided dice. What's the probability? It gets a sum of 7. So if you've played like Monopoly or something before, you know about throwing 2 dice and adding them up to see how many spaces you got to move. Now you could add up a 1 and a 1 and get a 2. You could add up a 1 and a 2 and get a 3. You might get a 4, a 5, a 6, a 7, an 8, a 9, a 10. Or if you get 2 6s, 11. If you get 2 6s, you'll get a 12. Those are the possible sums. So if you're going too fast, you'll say, well, the probability that I get a 7 is, let's see, there's one way to get a 7 out of, what is that, 11 possible sums, which would be like 9.09%. Question mark? And what's the question mark for? What's the question we need to ask? Always, we need to be careful. We need to ask, these outcomes, are they equally likely? And they're not. Why aren't they? Well, think about how many ways can you get your dice to add up to 2. You would have to roll a 1 and then another 1. Well, how many ways could you get your dice to add up to 3? You could roll a 1 and then a 2, or the dice could be switched around and the first one comes up a 2 and the second one comes up a 1. Now, if you don't like that very much, think of how many ways you could get a 4. You could get a 4 by getting a 1 and then a 3, right? Or you could get a 2 and then a 2, or you could get a 3 and then a 1. So the point is, these are not equal size thingies here, right? Fractions are supposed to have equal size slices. In terms of probability, probabilities are supposed to have equally likely outcomes. Getting a 4, there's more than one way to get a 4, There's only one way to get a 2. There's only one way to get a 12, but there's more than one way to get a 4. There's a lot of ways to get a 7. These are not the outcomes we want to use when forming our fraction, when forming our probability. We can't use these. Nope, can't use them. We can try to use this eraser, but it'll take a while. Okay, so what are we going to do instead? What we have to do is we have to really break down the action carefully. Break down the action carefully. And we got kind of a hint of it when I said when you roll a 3, it could be a 1 and then a 2, or it could be a 2 and then a 1, right? So in other words, you got to think about the 2 dice kind of separately. So maybe the first die is a 1 and then you get a 1. Maybe you get a 1 and then you get a 2, a 1 and then a 3, a 1 and then a 4, a 1 and then a 5, a 1 and then a 6. That's 6 possible outcomes, and those are all the same chance of happening, right? You could get a 2 and then a 1, or a 2 and then a 2, or a 2 and then a 3, or a 2 and then a 4, or a 2 and then a 5, or a 2 and then a 6. 6 more possible outcomes. These are all equally likely. There's only one way to get a 3 and then a 1. There's only one way to get a 3 and then a 2. There's only one way to get a 3 and then a 3, and so on. 3 and a 4, 3 and a 5, 3 and a 6. You could get a 4 and a 1, a 4 then a 2, a 4 then a 3, a 4 then a 4, a 4 then a 5, a 4 then a 6. You could get a 5 then a 1, a 5 then a 2, a 5 then a 3, a 5 then a 4, a 5 then a 5, a 5 then a 6, a 6 then a 1, a 6 then a 2, a 6 then a 3, a 6 then a 4, a 6 then a 5, a 6 then a 6. Those are all the equally likely outcomes. 36 if you count them. 36 total outcomes. Equally likely. We listed them. That's what I call breaking down the action carefully. So, okay. Now, we can go around, trying to figure this out. The probability of getting a sum of 7, well, you would have to have the number of 7s or their total number. And we just figured out the total number of equally likely outcomes is 36. So the next question is, how many of these are 7s? When you add them up, a 1 and a 6 gives you a 7. 2 and a 5 gives you a 7. 3 and a 4. 4 and a 3. 5 and a 2. 6 and a 1. Those are how you get the 7s. There's one of it. Hey, you. Hey, you. Hey, you. What are you doing? Okay. There's 6 of those. So the 6 goes there. So the probability of getting a sum of 7 on 2 dice, 2 6-sided dice, is actually 6 out of 36, which reduces, if you cancel 6s, to 1 in 6. If you do 1 divided by 6, you'll get 0.166666666 repeating. And if you do one of these deals to make a percentage out of it, I don't know, you might call it 16.67%. So 1 in 6. See, in this case, doesn't 1 in 6 seem a little easier to think about than a 16.67%? That's why we do a lot of converting back and forth. We don't just pick one and stick with it. We say, well, 1 in 6. What percent is that? 16.67%. Oh, interesting. I like the 1 in 6. But sometimes 1 in 11. What is that? That's a 9.09%. You might like thinking of 9%. I don't know. Whatever. Equally likely outcomes. It's with us again. Okay. One more example. We're going to bring it on home with this one. Let's go purple. So, back to the boys and girls thing. Now here I'm saying let's just pretend, for the sake of argument, that the probability of having either a boy or a girl is 50-50. 50% each, okay? Just to keep the math a little easier. We know that it's a 51% for a boy and a 49% for a girl, but don't worry about it. We'll just say it's a 50-50, okay? Pretend you're in a different world where it's a 50-50. Fine. So, here's the issue. You're told that there's a couple here and has 2 kids, 2 children, and one's a boy. They got 2 kids, one's a boy. Maybe they brought one of their boys with them or whatever. So what is the probability that the other is also a boy? That's the question. I'll just ask you to think about that and throw an answer down. What do you think? Couple has 2 kids. One's a boy. What's the chance the other is also a boy? Are you thinking it's 50% that the other is also a boy? Well, your logic, I suppose, would be that it's a 50-50, right? So what is it? I don't know. It could be a boy. It could be a girl. It's a 50-50. So I guess it's a 50-50. So it must be 50% that it's a boy. Right? That's what you're thinking. It's not quite right, though. See, and then this is the value. I hope you're kind of excited by this opportunity to say, what? What's going on here? I need to know. This is the value of studying math. See, it makes you more cautious. It makes you more careful. It makes you a little less quick to accept what someone else is saying, a commercial or whatever. It makes you a little paranoid. That's the drawback. But you can win a lot of money at the bar this way. Okay, so anyway, see, the question is, when we go listing the outcomes, right? What would be considered a possible outcomes? Well, we're told that it's a family with 2 kids. That's what we're told. A couple has 2 children. Okay, if they got 2 kids, what could have happened? It could be that first they had a boy and then they had another boy, right? That would happen. It could be that first they had a boy and then they had a girl, right? There's not that many things that can happen. We can just list them out. It could be the first one was a girl and then they had a boy, or it could be the first one was a girl and then they had another girl, right? Isn't that basically what you can do? If you have 2 kids, it's either boy and boy, boy and girl, girl then boy, or girl then girl. One of those. Hold the boat. Look at this. They said something else. Close reading is key. They said something else. They said one of which is a boy. One of which is a boy. Well, I guess that rules that out, doesn't it? One of which is a boy means we can rule this out. It is not a family of 2 girls. It is not a family of 2 girls. So, back to our question, what are the possible outcomes? There's only 3, not 4. There's only 3 possible outcomes. They either had a boy and then a boy and then a girl, or a girl and then a boy. Okay, so out of these 3 possible outcomes, what color do I need? Bring it on home in light green. That one's a boy, that one's a boy, that one's a boy. Okay, so in these 3 families, they all have a boy. What's probably the other is also a boy? That one's also a boy. That one's not, that one's not. So it's actually one way you can do it out of 3 total. It's a 1 in 3. How about that? It's a 1 in 3. Now, isn't that something? Doesn't that make a really good test question? I think that makes a grand test question. Grand homework question, maybe. Okay, anyway. So that's cool. That's really cool. So again, the point is, when you're counting probabilities, don't go too fast. You're going to make a fraction. You're going to put one number over the other, but you have to be careful, slow, consider, am I looking at equally likely outcomes? Or in this case, you might even say, am I taking into account all of the information they gave me? They said one was a boy, so that ruled that possibility out. We only had 3 possible outcomes. One of them worked. 1 in 3 chance that the other is also a boy. Okay, I think that's good. How long did I go there? 43 minutes. I'm getting long-winded. I gotta stop this. All right, see you next lecture.